project is about the link prediction with graph neural networks and knowledge extraction. For many real-world tasks can be transformed into graph-related tasks. There are certain drawbacks in graph neural networks technologies. One of them is the shallow neighborhood. Another drawback in GNN is the structural issues. We developed a novel approach for addressing this problem. We will show that it leverages each node's extracted knowledge. We improve the scalability via sampling. So our method actually draws inspiration from graph neural networks. The first area is the graph neural network, which includes several technologies such as GCN. We actually didn't use this method in this project. And the second technology is GraphSage, which introduces a spatial aggregation of local node information by different aggregation weights. And the third method is a GAT, which proposes an attention mechanism in the aggregation process by learning extra attention weights to each node neighbors. There are several limitations of graph neural networks, such as Laplacian smoothing and the deeper version of the GCN.
To address the drawbacks mentioned above, we proposed a method called link prediction with knowledge extraction, that the graph neural networks can be implicitly guided by high-level extracted knowledge. The advanced knowledge extraction methods such as BERN can extract high-quality knowledge, and NER example by BERN is shown in this figure. But as mentioned before, it is expensive to extract high-level knowledge for all nodes. Thus, in we only extract sample fraction of nodes. The number of samples is shown below, where n is the number of nodes in G. Then we extract knowledge for the sample nodes by using methods such as NER, which is denoted as set S for NS random nodes. Each item Si is a set of knowledge attributes, and let's assume Si is associated with nodes Vi belongs to a bigger Vs, where the bigger Vs is the overall sample node set. To give a high-level summary of in the paper of the process steps, first, only a sample fraction of nodes are extracted. Secondly, we use Jacquard similarity to calculate the similarity between various article entity sets and add an implicit edge if the similarity is greater or equal to a threshold value. And finally, we combine the implicit edges with the training of GNN.
The dataset we use COVID-19, which is a biomedical dataset. It contains thousands of articles. We utilize the abstract, its bag of words representation as the node features. Graph is very sparse and it is very disconnected. For the metrics, we use the accuracy and the ROC-AUC score, which is often utilized for the link prediction task. For the GNN hyperparameters, we use the usually settings. For the GNN layers, we utilize GraphSage and GAT, which is often utilized in the link prediction task. For our method hyperparameters, it is different for different GNN layers. At first, as shown in the table in the bottom, we perform our method's best performance. We run each model for more than 5 times. In the left figures, we can see that for both GAT and GraphSage, our method in the average accuracy and also the minimum and max accuracy, it can beat the baselines. Basically, we have 2 data objects. The first one is called Burn.pkl, which contains the Burn entities. And the second one is called the reference tensor.gpco. It contains the whole graph and also the features in PyTorch tensor format. And also we have the entity.py. It will perform our method, for example, such as sampling the random code and the implicit knowledge edges. So basically, we have 2 metrics. The first one is ROC-AUC. The second one is accuracy. From the learning, we can see that both the ROC-AUC score and the accuracy is increased during the training. In conclusion, in this project, we propose a novel idea to implicitly incorporate the rich knowledge during the GNN message passing and effectively reduce the negative influence of and limitations of GNN layers and the issues of real-world link prediction graphs.